Swayam Prabha. Digital India. Educated India.
So in most of the spray applications, one of the inputs that we have to give to the problem is what is called as the initial spray droplet size distribution. In fact, when we look at the spray distribution function, it says we need to actually look at a bin of certain droplet radius and a bin of certain droplet velocities and a bin of certain droplet locations and so on. So typically, for example, you do something called a PDPA experiment in order to try to find out what is the droplet velocities and as well as droplet sizes simultaneously. So it's possible for us to actually measure them together, but you do that in a particular experiment and then you want to use that as a inlet condition to, let's say, a flow field in where for example this burner is now fitted into a combustor or a reactor and so on. So obviously the positions are not going to exactly be the same. You are going to only derive statistics out of it rather than exactly know what the positions of the droplets are in this experiment. So the best thing that normally people do is if you now want to fit a certain burner with a let's say oil spray, you at least have to know what will be the droplet size distribution at the inlet to this combustor from the burner exit, and therefore we have to look, we need to know what is called as the initial droplet size distribution that is usually obtained empirically. Of course, there are recent efforts to actually try to computationally predict this as well, by taking into account the shearing of liquid sheets or liquid rods, liquid tubes kind of thing, by the aerodynamic as well as hydrodynamic effects and so on. But of course there is a lot more that needs to be done computationally in order to be able to predict droplet size distributions accurately. At the moment I think they are mostly used for design of atomizers from a qualitative viewpoint, like for example if you now change some parameters, how does it affect the droplet size distribution kind of thing, but they are always benchmarked and calibrated against experimental data that is obtained. So this is basically like let's say used with a symbol G of RL. With this you should actually be able to obtain several spray properties. So the spray properties are based on the droplet size distribution, or integral 0 to RL drl drl. This actually is the total number of droplets of radii less than RL. And you can also look at the volume. So 4 over 3 pi integral 0 to RL cubed G RL drl, that's the total volume of droplets of radii less than RL, right. Now many times we use this quantity called the Sotomayor diameter, or SMD, which can be written as in the form of integral. It can be written as integral 0 to let us say certain maximum RL that you have in the distribution, RL cubed GRL DRL divided by integral 0 to RL max RL squared GRL DRL. So notice that you are going to get something like an average radius out of this, but SMD is actually a diameter, so you have a number 2, a factor 2 there to make that a diameter. Essentially, or okay, there is one more way by which you can define this, which could be more familiar, that is twice of sigma over all I Ni RLi cubed divided by sigma over all I Ni RLi squared. Now this is actually something that is more familiarly used, because typically what we do is we now have a bunch of droplets and then we now try to size them into bins of certain elemental radius bins, and then you now count the number of droplets that are there in each bin, that is the Ni, and so on. So you essentially get what's called as a histogram, and if the bin size is very small, that means you are now counting a large number of droplets and then placing them over smaller resolutions or higher resolutions of radii, then this can actually become an integral, right. So the integral definitions are typically when the histogram bin sizes are small, and you can now try to fit a curve out of the histograms rather than keep them as histograms themselves, but this would actually hold if have histograms. And essentially the idea of both the sort of mean diameter in both these definitions is we are looking at basically a ratio of total volume to total surface area, right. So ratio of total volume to total surface area. So you know, when you now have atomization of a spray, and if the atomization is very fine, then the total surface area is actually very large. Okay, so if you now have a larger and larger atomization done, of course the volume corresponding to it is also preserved. So typically if you have the same radius for all droplets, then it didn't matter, you will get the same mean radius regardless of how you actually averaged. You did a arithmetic average, let's say, so for example this is the total number of droplets, and then if you now have a integral 0 to RL or RL max, RL GRL DRL divided by integral 0 to RL max GRL DRL, right. That would actually be the arithmetic mean, and this would be like the sort of mean diameter. You could also have like a weight mean diameter and so on. So all these things will actually amount to the same if the radius of all the droplets are the same, okay. But when you don't have the radii of all the droplets, progressively higher and higher weightages is going to shrink the size, the average size. Basically here in this case you can clearly see that you have a large surface area, then that's going to actually pull down the mean, right. So typically what's done in order to get the smooth curve that we talk about is from the histogram data you can now fit a what's called as a Rosen-Ramler distribution. So this is very popular. So the generalized Rosen-Ramler distribution for sprays is so this is a distribution function G of RL is equal to B of RL to the power T exponential negative A of RL over S. So here A, B, S and T are constants that are used to fit the data to this distribution. So A, B, S, T or constants, constant fitting parameters. Right. Now there are special cases. So T, for example, T equals s minus 4 is Rosen-Ramler distribution, that is the original Rosen-Ramler. T equals 2 corresponds to what is called as a Nukiyama Tanawasa distribution, and S equals 1 is what's called as a chi-square distribution. And so on. So you now have these 4 constants. What we should be looking for in trying to fit curves is 4 conserved parameters. So essentially the 4 characteristics that we should be looking for is 4 characteristics. N is the total number of droplets, which is something that we saw, but here we try to take all droplets. So 0 to infinity G DRL, the total number of droplets, total number of all droplets. Then you have a mean, which is defined as 1 over n. This is the arithmetic mean, 0 to infinity RL G DRL, which is the average droplet radius. We can simply say size. Sigma, so when somebody says size, usually they talk about diameter, that is the colloquial parlance, but in this case we are actually referring to radius. So keep that in mind. Sometimes these definitions might be different, and then you're off by a factor of 2 many times, so you know what to suspect. So sigma equals 1 over n, 0 to infinity RL minus the mean, or the whole squared GDRL, which is the standard deviation and finally you have the skewness, which is S times sigma cubed equal to 1 over n integral 0 to infinity RL minus mean of RL, the whole cubed G DRL, which is the skewness. So if you're now able to actually get some data with which you know the mean, the total number and the standard deviation and the skewness, you can fit the distribution that satisfies these things, right, and then try to obtain the constants, and then now you have a curve that is a standard template that follows the standard template. Good. So with this, what we then do, we can do is once you have a good description of the droplet size distribution, we now look at the conservation equations for a spray flow. So conservation equation for spray flow including combustion of sprays. So conservation equations. here we want to now define rho f as the mass of the gaseous mixture per unit volume of the two-phase mixture. So you now have a two-phase mixture with droplets in there and in gas, and the gas in turn is a mixture of gases. Alright, so this is basically the mass of the gaseous mixture per unit volume of the two-phase mixture. The rho g is actually the gas density. So it is to say that rho f is kind of like taking into account the two-phase part of it, but rho g is without taking into account the two-phase part of it, right. So if you want to distinguish these two, then rho f divided by rho g is nothing but 1 minus integral, should say actually double integral. We want to go back to the spray distribution function, taking into account different velocities for different droplets. So then that would be 4 by 3 pi RL cubed divided times f d RL du. Then the overall continued equation for the gas is partial derivative of rho f with respect to time plus a divergence with respect to x of rho f v vector is equal to negative double integral rho l times 4 pi RL squared RL dot f d RL du. So here what's going on is you now this is basically the rate at which the liquid evaporates or its surface regresses and then produces gas, right. So since this is a this is dRL by dt where the RL decreases as time increases, you need to have a negative quantity to make sure that you're adding mass to the gas. So this is basically the this is coming from reduction in the liquid mass due to droplet evaporation causing gas phase density variation. Right. Basically what we are saying is whatever mass that is lost by the liquid is added to the gas because mass has to be conserved, right. So the momentum conservation is rho f partial rho f times partial derivative of v vector with respect to time plus rho f v vector dot divergence with respect to x of v is equal to minus divergence with respect to x of the stress tensor including the normal stress, namely the hydrodynamic pressure, right, plus rho f sigma over k for species, yk fk, that's the body force. So we will name these once we finish writing the full equation. Then you have another term which is coming from the evaporation, 4 by 3 pi r L cubed. Oh no, this is the drag on the droplet. This is the drag experienced by the droplets from the gas, and in turn the droplets exert an equal and opposite drag on the gas. Okay, and we will talk about that, plus the thing that I was just mentioning, which is the momentum that is imparted due to droplet evaporation. So that comes from rho L 4 by 3 pi RL cubed RL dot U minus V F DRL du, right. So here Fk is the force per unit mass of the kth species, that is basically the acceleration experienced by the kth species. This typically is different for different species. If you have things like ions that are subjected to an electric field or magnetic field and so on. So of kth species, G is the drag force that's equal to 3 over 8 rho g over rho L modulus of the relative velocity times the relative velocity to give you the direction divided by RL times CD. Now CD is the drag coefficient depending on Reynolds number and mass transfer number. So it will also depend, because you now have an evaporating droplet, so it depends on mass transfer number, Reynolds number Re. So Reynolds number is Re equal to 2 RL, that gives you the diameter times density times the relative velocity magnitude divided by the gas viscosity. So that's taking care of this term on the right hand side, and finally this term is basically the momentum transferred to the gas by the vaporizing mass, because when the gas comes out of the surface of droplets, it now imparts some momentum to the gas around. So this momentum transferred by the vaporizing mass to the gas. Similarly, we could also write the energy equation. Partial derivative with respect to time of rho f times hf plus v squared by 2 plus divergence with respect to x of rho f v hf plus v squared over 2. This is the total energy equation, that means it includes the kinetic energy also, equals minus divergence with respect to x of q vector minus the stress tensor dotted with gradient of v. So this is basically a tensor, gradient of a vector is a tensor, the stress tensor is a second order tensor, therefore this is actually a double dot product, okay, giving rise to a scalar finally as part of the energy equation, plus the partial derivative of pressure with respect to time, that's coming from the PV work, and then you have the effect of body force over k yk fk vector dot v plus capital Vk. This is the diffusion velocity of the kth species. Keep in mind this is what the momentum equation is all about. So this is the total energy equation. If you got the thermal equation, thermal energy equation alone, that would be by dotting that with V, which is the mixture, gaseous mixture average velocity. So that this might go away, but this would still stay, right? So the body force acts on the actual velocity of the species, which includes the diffusion velocity as well as the average velocity of the mixture, the gaseous mixture, minus, then you have a couple of terms that are specific to droplets. So you now have a rho L 4 over 3 pi r L cubed G U, this is the work done due to the drag force, times F drl du minus integral rho L 4 pi RL squared, that's the surface area, times RL dot H plus U modulus squared times F drl du, right. We need to go back and check here. I think this must be 4, this must be 4 pi RL squared, because we are looking at the surface evaporation. Okay. And then finally we have the species conservation, which is rather straightforward. With respect to time, partial derivative of rho f yk plus divergence with respect to x of rho f v plus capital Vk yk. So this takes care of the diffusion mass flux, right, equal to the chemical production minus, we also have production of the kth species of the gas from droplet evaporation, right. So rho L 4 pi r squared RL squared RL dot omega k F drl du, where omega k is actually the radial mass flux of kth species from droplet surface. Okay, just could squeeze some space there for writing that. So what then happens is, if you now write out these equations, this is sort of similar to the governing equations that we wrote for a homogeneous combustion, that means all species being gaseous, but here this is for heterogeneous combustion, where you are now throwing in a bunch of liquid droplets, typically fuel droplets, and in each of these equations you can see that there is a source term that is coming out, at least one or two source terms that are coming up because of the droplet. That means the droplet would now add mass to the gases, it could now impart momentum in a couple of different ways, energy in a couple of different ways, and also throw in a particular species into the gas, and therefore comes in as source terms in the equations. Now what you have to imagine here is, let us suppose that we try to solve this for a typical flow field which is quite turbulent. There are some very nice research that have been done which now begin to look at what is the effect of the turbulence on these droplets and what is the effect of these droplets on the turbulence. Okay. So typically what happens when you now have a locally high Reynolds number situation based on the mean, based on the relative velocity between the gas and the droplet velocity, you could now have a wake that is shedding behind the droplet. Okay. So you now have a overall turbulent field into which now the droplet is actually moving following the turbulent flow around, but as it is moving it is also producing a wake behind it, and this wake is obviously of length scale of the order of the droplet size rather than that of the characteristic dimensions of your combustor or your burner or something, which the overall turbulence, the prevailing turbulence is of a length scale of. So what happens is, you now have these multiple length scales of turbulence, the larger length scale corresponding to the combustor geometry and the small length scales of the wake turbulence from these droplets. So a snapshot, for example, if you were to now do something like a PIV of this and take like a planar data of what the flow field is, you will now have like a large scale motions captured over the larger area with like pockets of intense small scale turbulence here and there, because the droplets have just gone past these planes here and there. So that's typically described as a Swiss cheese, because if you now take like Swiss cheese, you now have these lots of these holes. There are these holes now filled up with, in this case, the droplet turbulence. This is pretty interesting. The other thing now, if you now begin to think about these droplets burning rather than just evaporating, and let us suppose that we were talking about the group combustion number, which now allows for individual droplets to have flames associated with them. We never really talked about what happens when you have droplets in motion, right? So the kind of even the kind of pictures that we drew were as if like the droplets were stationary, and you have an envelope flame that is spherically symmetric about the droplet, assuming the droplet itself is spherical to begin with. That's all right, but when you now have a droplet in motion, because of the motion the flame now becomes asymmetric, right? So a simpler experiment for that would be, if you now have a droplet and then you have a let's say a gas flow that's coming from the bottom, you now have a flame that is now getting elongated along the flow direction, right? And you could still think about something like a envelope flame that is enveloping the droplet all around but getting elongated along the direction of the flow, right? But then as you now increase the relative velocity between the droplet and the gas, you now get into a situation where you no longer have an envelope flame, you now have what's called as a wake flame. That means So if you now have a droplet and then you have a flow relative to the droplet, airflow relative to the droplet coming up, you now have an envelope flame that is enveloping this and elongating in the direction of the flow. This is what we would call as a envelope flame. And if you now have a greater relative velocity between the two, you actually begin to have only a wake flame. That means the flow goes around and actually causes like a liftoff of the flame, similar to how you have lifted flames. You now have the flame getting really confined only to the downstream part, which is what is called as a wake flame. So this is something that typically happens in these cases. That's a droplet, and let's see that the flame there behind you. Right. Okay. I want to stop talking about droplet combustion, but we are still in the subject of what's called as heterogeneous combustion. That means we are talking about some of the reactants or some of the species, chemical species in general, are in different phase when compared to the others, right. So far until we were talking about droplet combustion, it was all homogeneous combustion. That means we were typically talking about all the species being of the same phase, and that's a gaseous phase. But the moment you start talking about droplet combustion, we are beginning to step into heterogeneous combustion. And yesterday we mentioned the situation of let's say cold combustion, where you have like single particle combustion rather than a cloud combustion. That is because of lesser volatiles. So I'll just quickly talk about cold combustion and other solid combustion. We also mentioned, for example, metal combustion, where it is similar to droplet combustion, because by the time the metals are actually burning, they melt, and so you have molten metal droplets that are burning. And it's, although it may seem like we are actually burning solids, in reality you might end up burning liquids. So if you now think about cold particles, the problem mainly with the cold particles is it's essentially twofold. One, it is okay, before we in the context of talking about cold particles, if you want to now go back to liquid fuels, you can still talk about something called single component liquid fuels versus multi-component liquid fuels. Okay, so what is meant by single component versus multi-component is, if you now take a fuel, for example, like methanol, okay, you're essentially talking about only one chemical composition, or only one chemical substance there. But if you're now looking at something like diesel, it's actually made up of a large number of different hydrocarbons, okay, and each of those different hydrocarbons has different volatilities, and you could now get into volatiles that are actually volatilizing from somewhere near the core through the less volatile substance and penetrating through that and then coming out as gas, right. So one of the dramatic examples for that is, for example, if you now have something called aluminized gelled kerosene. Okay, kerosene itself is a multi-component fuel. On top of it, you now, let's say you try to gel it with aluminum, and aluminum is less volatile obviously when compared to kerosene. So what happens in these kinds of situations where you have a mixture of materials that are of different volatility is the more volatile substance, so the less volatile substance will actually begin to accumulate on the surface as the surface is regressing, right. And as it now accumulates and the surface is regressing and shrinking, the density of the less volatile substance actually increases, and it actually begins to form more like a shell. For example, in the case of aluminum, it could even get sintered together like a shell, and when it's sintered, it's like a porous structure through which you now have the more volatile substance get evaporated, right. At some stage, this shrinking continuously will now cause this, and then of course you have more and more aluminum reaching the surface, right, from within, and therefore you now have this shell actually kind of harden. You don't necessarily have it porous anymore, and you now have a gas, because the more volatile substance has actually evaporated from within the shell, and it now starts acting up with pressure, right. So when you now tries to pressurize the shell breaks, and then it now becomes smaller fragments. So similarly, this is quite dramatic when compared to that. If you now simply have multi-component liquid fuel droplets, that means you have everything is liquid, nothing is really concentrating and forming a hard shell there. But if you now still look at liquids, the more volatile ones can actually volatile from the core and bubble through the less volatile ones, and can cause what's called a secondary atomization. That means it now shatters the less volatile ones into smaller droplets, which from a single parent droplet. So the single parent droplet itself was actually obtained by atomization, but then you now have a secondary atomization because of this. So such things are possible. When you now look at coal particles, you have a similar scenario where it's not really the coal particle is not a single component substance, right. It's a solid particle, all right, and typically you pulverize it into very small sizes, but you're essentially going to have a bunch of different things. First thing, you have a lot of moisture, which is pretty bad because this is not going to burn, right. Then you have what's called the volatiles, which is what is exactly going to burn, right, and burn fast, and or evaporate fast, or get released into the combustion zone quite quickly. Then you have the minerals, which are bad because they are not going to actually aid the combustion, but they are going to actually finally bring in ash and what's called a slag. So this ash could in the combustion zone become like a molten region, and then as droplets or liquid molten liquid form, they could go and get splashed against the combustor walls and so on. So this produces ash and slag, and then of course you also have char. So this goes through a solid phase combustion and gives rise to a residue, and so effectively you're now looking at only two parts of this that are giving rise to energy. The other ones could actually soak up energy, alright, and this is pretty important because in the case of Indian coals, which is and India really relies a lot on coal, and there is a lot of coal reserves here for quite some time that we can burn, but it is all very high ash content, okay. So the ash content could be as high as somewhere like 30 to 40%. It's almost like we have coal and ash rather than ash and coal, okay. So that's a kind of situation we have as far as coal is concerned. Similarly, you can also think about this sort of a composition for biomass, okay. So if you now think about biomass, which essentially is let's say the most commonly encountered biomass is wood, but then you can also come up with all kinds of things, like for example even rice husk is considered like biomass, okay. So you can burn any of these things. A lot of agro wastes can be used in incineration or gasification. There are lots of technologies that are getting developed through these things. So typically again you have to characterize what's the moisture content, what's the volatiles content, what is the minerals content, what is the char content. So doing this kind of thing is what's called as a proximate analysis, trying to find out what are the different percentages of these different things, and then in turn you also have to find out what is the elemental composition of the energy containing constituents, and that is what is called as the ultimate analysis, right. So typically one of the major problems with biomass and coal, more with biomass because you have varied kinds of biomass in the first place, but even for the same kind of biomass and for coal the problem is different locations where you mine them or where you what do you call harvest them, you will have different compositions of these. So you have to do the proximate and ultimate analysis for these first to get an idea of what kind of energy content they have and what kind of ash problems you are going to face and so on in these things. But then once you are in a position to actually do like pulverized coal particles, then the analysis is not very different from what we have done so far, and it all takes us back to having diffusion flames or premix flames and so on. Of course these things typically will be turbulent flames, and we will talk about a little bit about turbulent flames, but within a gaseous framework, okay, in the next few days. We'll stop here for the day.